Hi everybody, we're almost done. In fact, there's really not that many slides left. So we'll just be going over those today. What important things do we want to talk about for like agenda stuff? There's an exam on Friday, so that's important. If you've not asked me to move your exam date and you would like me to move your exam date, please do that by tonight so that I can do that in a timely manner. I tend to do those at the end of the day as the last thing that I do for work. So, like, for example, I will probably grade stuff after this. I'm still grading all of your labs and things like that. And then before I go to bed, I do all the like Canvas stuff where I have to like click buttons and set all the things. So that'll be done probably later tonight when I'm done. Unless I take a break and like it's just something I do. So make sure you send that a request to me, and I will get to it as soon as I can. There is a lab number 5, which we talked about. Lab number 5 is kind of a review of the first X labs that we did. There's nothing new in lab number 5. It is literally just data, and like we basically give you simulated wine, like from a vineyard or something like that, and we say, okay, analyze this for these 3 things. You're going to do calculations just like you would have done in labs 2 and 3. Maybe a little bit from 1 also. And that's due on the date in the syllabus. And then there's a final exam next week, and a review session scheduled in the syllabus as well. So this won't be the last time that we meet. There will be a review session next week, and then that's it. We're done. So let's go ahead and... excuse me, I need to drink more water. Oh no, I'm out of water. We'll come back to that in a little bit then. Okay, so let's go over SP hybridization. We did SP2 hybridization. I don't know why I put my tablet away. Hold on. There's my tablet. All right. We talked about SP2 hybridization, where I had to save a p orbital. With SP hybridization, I want to make 2 pi bonds. So I need 2 orbitals that are unhybridized p orbitals. So when I hybridize, we're going to hang on to these orbitals and leave them as they are. These 2 will go into the blender. There you go. You don't have to blend very long for 2 things. And when I have 2 orbitals, these will be geometrically arranged as 2 domains that are basically opposite of each other. And that looks like this. So we end up with a linear arrangement where I'm going to have my overlapping orbitals be, like, say, here's where my overlap would be if this is one atom and this was another. It'd look like that. And then what other orbitals come out of this, I don't know. Who knows? If we wanted to draw the balloon structure for C2H2, in fact, you know what I could do? Well, no. I mean, we've already kind of drawn this. That's okay. I was going to have you draw it as practice, but that's okay if you just want to... If we just want to see it. So, you can see here. Let me get a color that will show up on this, though. That should be okay. So, I'm going to draw... Here is one of my pi bonds here. So, my p orbitals go up and down, and then they overlap like this. In this orientation. And then I'm going to choose another color that should show up well on this. So we'll do orange here. This other... Oh, of course my tablet's going to start doing this because it's stupid and dumb. There we go. I'm trying to go slowly enough so it doesn't spike and freak out like that. There we go. So there's my other p orbitals that are in the orthogonal plane to the plane that my initial p orbitals were in. So these are all perpendicular to each other, 90 degrees. That's what orthogonal means, is 90 degrees apart. And then the purple orbitals in the middle, which we'll do in a different color again. Let's do blue like this. This right here, this is my internuclear axis between carbon and carbon. And you can see I've basically made coordinate axes. I got X, Y, and Z. Or, oh god, my Canadian slipped out there. X, Y, and Z. So my unhybridized p orbitals remain in whatever orientations they would be, which would be px, py, or pz. I'm going to hybridize the one orbital that goes along the internuclear axis. I'm going to leave the other ones the same, and they're going to participate in pi bonding. The sigma bond occurs in the middle with my hybridized sp orbitals overlapping. And the electrons just go in those spots. So that's what a triple bond looks like. Where is the electron density around the triple bond? It's basically completely surrounding the molecule. There's a lot of electron density all around it, holding the molecule in a very short and tight bond. Now, I want to say earlier in the quarter I asked you, can we make a quadruple bond? And I said no, because the bonds have to go in straight lines. You can kind of see here, there's really no opportunity for me to make a quadruple bond, because I don't really have space to use. Now, if I was bonding something that had d orbitals available, then maybe I could, because remember that d orbitals kind of look like clover leaves. Like, here's what a d orbital looked like. I mean, you could see that I could maybe fit that in, like, say, here. In this space. And metals actually can do this. So you can, oops, oh no, I've ruined everything. Let's just go to the next slide. You could actually make a quadruple bond using d orbitals in compounds that have d orbitals, such as, say, like transition metals. And if you are interested in, like, those weird oddities that can happen from overlap, then taking third and fourth year inorganic chemistry might be up your alley. There's a lot of really cool stuff that we can do with d orbitals in transition metals, but we don't cover it in this class. What happens when we have elements that make more than 4 bonds? So things that make, oh, excuse me, things that make 5 or 6 bonds, for example. So the purple ones are s orbitals. The blue ones are actually s orbitals here. The purple are the sp hybridized orbitals. Sorry, I just looked over and saw that question. So yeah, the H atoms over here have 1 s orbitals. Those are blue. Remember that s orbitals are always spherical. If we end up with anything that looks like a bowling ball or a bowling pin or whatever, that has to be either a hybridized orbital or a p orbital. All right, so what we're going to do, for anything that makes 5 bonds, what we need to do is we need to have 5 unpaired electrons. So we're going to do the following. I need to have d orbitals available to do this, which means that the requirement for elements that want to make 5 or 6 bonds is that they must be in n equals 3 or higher, because you need to have n equals 3 to be accessing d orbitals. So let's suppose I have, like, phosphorus. Phosphorus does PCl5, right? So if I have phosphorus, which looks like this, if I blend these 5 orbitals together, this is what I get. And then my 5 electrons would look like this. And now what I can do with these orbitals is that I can use them in a trigonal bipyramidal arrangement, which would look like I have a trigonal planar, and then above and below, like this, where I could make 5 bonds. Same thing with 6 hybridized orbitals. I just blend in an extra d orbital. I can make sp3d and sp3d2 orbitals here. Again, the names are just what orbitals are you putting in. How do you know which orbitals to put in? How many do you need? If I need to make 6 bonds, I'll put in 6 orbitals. I will get 6 out. What orbitals I put in? I just go bottom to top here. So sp3d2. And so what do those things look like? Here's some examples of these. So arsenic, for example, in arsenic pentafluoride here, ASF5, here is the Lewis structure, which we're just drawing with a random geometry. But in reality, what it looks like is we have this trigonal bipyramidal center, where here's my arsenic. I have sp3d hybridized orbitals bonding with fluorine. Now, this text says that fluorine is unhybridized, but remember, when we make bonds, we want to hybridize stuff. So this should actually be sp3 for fluorine. And then over here for sulfur, we get this octahedral arrangement with the yellow orbitals in the middle are sp3d2 because it makes 6 of these balloons. I'm trying to think of the correct name for it. Lobes is what I want. 6 of these lobes that we can use for bonding. And again, outer atoms are hybridized because we need to hybridize in order to form bonds. All right. This is the last slide for hybridization. This is the important slide, really. Every geometry corresponds to a hybridization that is required. So, for instance, if I want to make a linear molecule, I have to have sp orbitals. Because the orbitals themselves are 180 degrees apart and conform to the linear arrangement. So it's sort of a cyclical reasoning here that's going on. I need something linear. It has to be sp because sp is 180, and 180 corresponds to linear. If I have a trigonal planar geometry, the hybridization would be sp2. So you can really just name these hybridized combinations with a corresponding geometry. And these will always pair up in this manner. There are 0 exceptions to this. sp3 is always tetrahedral. If it's not tetrahedral, it's not sp3. It would be something different. So if you go back and review the geometry slides, and a lot of that felt like, well, I don't know why I have this shape, or I don't know when to use this shape, then this will probably start to help a little bit. These two topics do go together in a way, which is why we do them together at the end. So now you can look at the Lewis structure and be like, okay, I have this pi bond, so that means it must be sp2. Therefore, this molecule must be trigonal planar. So geometry and hybridization go hand in hand. And it's because they're models that are basically the same model. So really what you need to know is just, for every given shape, there is a hybridization. Make sure you draw the Lewis structure correctly so that you can get the correct hybridization. All right. So what I want you to do is I want you... Oops, I didn't mean to go past that. I want you to draw the Lewis structure for each of these molecules. And then I want you to identify the hybridization of the underlined atom. And before you do that, actually, I think I might have an issue with one of these. Hold on, let me... Is XEF6 weird? Yeah, it totally is. Okay, oops, I don't want to watch a video. I just wanted to look up its Lewis structure. Okay. So, you know what we will do? We won't do that one. Let's do one that I know is not weird. Let's see here. I believe this has the hybridization I want. Yeah, that'll work. Okay. All right. Go ahead and do this molecule instead. And we will go over all the answers in just a second. Oh, you know what? Hold on. I'm so indecisive here. Let's do that instead. That's better. That's a structure that makes sense to me. Okay. Yeah. I'm trying to give you something that, because XeF6 actually has like a weird extra hybridization. It's sp3d3, which we don't talk about. And then XeO2F2 has 5 things around it, but you're still making pi bonds. And I just don't want to go into the, oh, we use d orbitals for that discussion. So there we go. Do that molecule instead. Do these 4 molecules. I'll shut up and let you draw. I don't really know how much time it's going to take for you to draw all the balloon diagrams. So I do want you to try these. So I'm going to say like 3 or 4 more minutes. And then we'll go over all the answers together. All right, 1 or 2 more minutes. We'll go over the answers here. All right, let's draw a bunch of balloon structures. So, oh, that didn't quite. I'll just do that for now. Okay. So the first thing that we need to do is draw the Lewis structure. And so I'm going to just, oops, I'm going to do nothing apparently. There we go. I'm going to just quickly draw that. Where'd my cursor go? Oh, I'm using the wrong end of the pen. That would be why. So there's the Lewis structure for HCN. And what we can see from this is that, let me get a darker color here. I need to make 2 pi bonds here, which means that this carbon must be sp hybridized. And that this must also be in a linear arrangement. So when I draw my carbon, I'm going to bond it to a nitrogen like this. So I'm going to draw, here's my orbital, and I'm going to have another orbital over there. So this is going to be my sp orbitals like this. And so I've got 2 electrons for my bond there. Here's the non-bonding electrons over there. And then hydrogen over here should kind of look like that. So there's my atoms that are in a line. And now I need to have my p orbitals. One pair is going to go up like this. And also down. So like that. And I have a pair of electrons in that. And then I have another pair of electrons in an orbital going in this orientation. And this orientation. And then I got to make sure that I can... that turned out okay, I guess. That looks alright. It should look pretty similar to our C2H2, except instead of a C, we have a nitrogen. And instead of an H on this side over here, this side right here, we have an electron pair. Oh, I didn't put my electrons in this. There we go. So those go in there. All right. So we've identified the hybridization. So carbon was sp. This nitrogen must also be sp. And then hydrogen is just never hybridized. It's always 1s. There are no orbitals to hybridize with. All right, so we got that one. I'm going to do these next 2 together because they're actually relatively simple. So we'll look at XEF4. And if we do the Lewis structure for XEF4, well, this one I actually don't have memorized, so it'd be 4 times 7. So 36 electrons. So the Lewis structure would look something like this. So I got 2, 4, 6, 8 electrons, 10, 12, 14, 16, 18, 20, 22, 24. Because I'm just doing octets, right? 8, 16, 24, 32. And then 33, 34, 35, 36. So that's what that looks like. So this would be 6 electron domains. 1, 2, 3, 4, 5, 6. So this must be sp3, d2. As an octahedral Vesper geometry. And its molecular shape would be square planar. And so what would that look like in a balloon diagram? So if I have xenon over here, I would just go balloon, 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 balloon. And then in 2 of those balloons, I'll put my electron pairs. And in the other balloons, I will just put fluorines. So, and to simplify, so I don't have to draw the entire sp3 for fluorine, I'm just going to do it like this. And that's what that would look like. And on each of the fluorines, there would be 3 other sp3 orbitals, like this, and they'd all have unpaired electrons in them. I'm just not going to draw that for all those because who cares? For IF5, let's draw the Lewis structure. So this would be 7 times 6 is 42 electrons. So there's 8. Oh my goodness, this pen. 16. 24. 32. 40. 42. So I still have 6 domains for my electrons. So when I draw... Oh, well, first my hybridization would be sp3, d2. There's 6 domains, so that's going to be octahedral. And its shape will be square pyramidal. So when I draw its Lewis structure, I have my iodine right there. And we're going to have 6 balloons coming out of it. Balloon, balloon, balloon. Balloon, balloon, balloon. And one of those will be an electron pair. And then the other ones just connect to fluorine. So same deal here. Fluorine. Fluorine. And you get the point, right? I'm not even trying to make this look good. I'm just sort of lazily drawing it here. I will rewrite my iodine in the middle, though, just so you can see it. And then the last one we have is triiodide. Why are we using iodine so much? Because it just makes a lot of covalent bonds. Triiodide has this as its Lewis structure. This one I've memorized. Oh my goodness. My pen is just... It's because I need to reboot the computer, I guess, but it's not registering every dot that I draw. So it's super annoying. So 5 electron domains around the central atom means that the central iodine is sp3 dehybridized, which makes it trigonal bipyramidal. And then 3 of those are electron pairs. So its molecular shape is actually linear. And we can see that if we do this. So I have 5 balloons coming out of iodine. So there's the 2 linear parts, and then we've got the trigonal part. And these all have electron pairs in them. And these other iodines are the ones that form the bonds. And then we would have the other sp3 orbitals around iodines on the ends. We can put the electrons in, but we don't care about that. We're just caring about the central atom. All right. At this point, I would actually say let's take a break, but there aren't really any more slides to talk about. Like, that's it. We're done. Hooray, we're done. Yay! We don't really go over molecular orbital theory, mostly because, like, you could spend an entire lecture on this. There's some interesting stuff in here. For example, oxygen is magnetic. Like, you wouldn't expect this. You could put oxygen in a magnet. And magnets occur when you have unpaired electrons. So what we do is, this is basically another way to draw, like, let me find a diagram that has it. Where's O2? There's O2. So we'll just fill in the electrons here. So this is another way of drawing electrons as opposed to having like an atom diagram going 1s to s2p. We would combine orbitals in specific ways, and we get these sigma, pi, pi star, and sigma star things. This will be useful to you in organic chemistry if you're going that far. And that we'll go over it again in organic chemistry, but if you're not in organic chemistry, you don't really give a shit, so. That is, oops, you know what we're going to do? We're instead going to go over here and hit this button. Yay! Oops, hold on, there's music here. If I can get it to stop, so. So wherever you are, whatever you do, celebrate, because we're all done. We've done all the slides. We've covered all the content. Hooray! There we go. It's not playing the music again. How many times do I have to freaking do this? Okay. There we go. Yay. That's it. That's all I have. Normally I do that and it works the first time and it doesn't take 5 tries, but, you know, what can you do? Gotta go out with a bleh. So, yeah, we don't have to take a break, or you could actually look at it in the perspective of that you're going to take a 1-hour break, because I don't have anything else to do. So that was Chapter 5. There is no quiz for Chapter 5. There will be some questions from the hybridization section and valence bond theory on the exam and also the final. Obviously, you do not have to draw a balloon diagram. We went over all the balloon diagram stuff just because I think it's helpful for you to visualize where electrons are to get a better understanding of geometry. I'm going to be around grading for the next hour, so if you have questions, you can ask me in the class Discord. I'm happy to answer them. I might actually sneak away real quick to go get lunch. I don't think I have very much food in my apartment because I need to go grocery shopping, so I might just run to the drive-thru real quick, get a burrito or something, and then I'll come back and answer any questions that anybody has. But yeah, that's it. 161 is over. Hooray. Yeah, I'll hit this button for music, and that's it. Thank you. I hope everybody enjoyed it, and I hope you learned something. Take care.